dealing with small samples when you're looking for inferences about two different population means or their difference. So our requirements are going to be we have to take randomly selected data samples from each population done in an independent manner. Both samples must have distributions that are approximately normal. So the populations that they're coming from must be approximately normal. Since we won't have a sufficiently large set of data, we're going to need to know that. And the third one is the population variances are equal. And again, even if the numbers aren't exactly the same for the variances, as long as they're not statistically different, then you're going to be okay. Alright, a confidence interval for the small samples. We have our point estimator, the x1 bar minus x2 bar. That's what's going to estimate mu1 minus mu2. We have small samples, so we're dealing with the t-distribution. And the standard deviation is going to be calculated a little bit differently. We're going to have a pooled variance. So this s of p squared is the variance of the pooled. So we take each variance, so the variance for sample 1, s1 squared, multiply it by its degrees of freedom, which is n1 minus 1, add that to the variance of the second distribution, or of the second sample, and multiply it by its degrees of freedom, n2 minus 1. And we're going to divide it by the degrees of freedom for the combined values, so n1 plus n2 minus 2, and if we add up these two values, that's what we'll get anyway. And our t-distribution is going to be based on this n1 plus n2 minus 2 degrees of freedom. So you can look that up with a chart, or those of you with the TI-84 can certainly use the inverse t function. Now, if you're using a chart, many of the charts won't go up as high as whatever this value is going to turn out to be, so you're going to have to pick one on either end of it. Now, there's also a calculator function that does the whole thing for you, so that will get the exact amount. Testing, again the same as we were doing before with large samples. We have the mean 1 equals mean 2 in all three cases, and if we're looking for a difference, we look at the two-tailed, so mu1 doesn't equal mu2. If we're looking for one specifically greater than the other, we choose either a left-tailed or a right-tailed, depending upon whether or not we believe the first population or the first sample mean, first population, is going to be less than the second one or greater than the second one. So the test statistic is going to be formed in the same sort of way as well. We're going to take the point estimator minus 0, because again we're attempting to determine whether or not the two things equal each other, not so much if they're different by a certain amount, although you certainly could do that, divided by the standard deviation of x1 bar minus x2 bar, which is this value here, the same as it was for the confidence interval standard deviation. And we're going to compare this test statistic to a critical value, or more to the point, a critical region. So the two-tailed, we're going to have an area on the left, area to the left of negative t of alpha over 2, and an area to the right of positive t of alpha over 2 that will be rejection regions. And both t of alpha over 2 and t of alpha will have n1 plus n2 minus 2 degrees of freedom, just as the confidence interval did. Left-tailed, we're looking to see if the critical value falls left of or less than the negative t of alpha, where the entire level of alpha is on the left, and the right-tailed is if our critical value t sub 0 is greater than the positive value, or the positive t of alpha, where the entire level of alpha is on the right. And once again, our p-value method works the same way. If the p-value is very low, less than our significance level, we'll reject. Otherwise, we will fail to reject.